Hi, my name is Nick Aarons, and I'll be going over my 6832 final project. For the final project, I decided to try to implement trajectory optimization for a two-dimensional hopper. The hopper has 5 degrees of freedom, with the x and y position of the leg, as well as the angle theta 1, the angle of the body theta 2, and the body's distance from the top of the leg, z. The actuators consist of a torque acting at the hip joint and a preload distance that acts on a spring in the leg. I chose to model contact forces as springs in order to soften the stiff dynamics. While not the most accurate, this assumption meant that I could define the contact forces in the dynamics equations rather than make the contact forces decision variables in the optimization problem, which I found to work better. To further help the nonlinear solver, I gave it a predetermined mode schedule of when the hopper would be in contact with the ground. This allowed different time steps to have different dynamics constraints corresponding to the different conditions of in the air versus in contact with the ground. Additionally, 3 different time steps were used as decision variables, corresponding to before, during, and after contact with the ground. This allowed the solver to stretch and shrink the contact to the required time while also placing it in the correct location relative to the start. To get the robot to hop up a set of stairs, I imposed the constraint that the initial and final velocity were the same, very similar to most gate problems. However, I gave the additional constraint that the final position was equal to the initial position with an additional displacement, allowing for the hopper to move up a step at a time. I also imposed dynamics constraints using a backward Euler approximation. This is the result for one step. Stringing multiple of these animations together shows the realistic scenario for the hopper going up a set of stairs. The other problem I investigated was an optimal fast gate for the hopper. To find this, I added a cost term which penalized low initial speeds, while removing the position constraint on the final state. The nonlinear solver was able to find a solution that covered nearly 7 meters in one hop. While I'm happy with the results of my project, there were a number of issues. SNOPT, the nonlinear solver I used, was incredibly finicky and often failed to find solutions when I changed the coefficients of the cost terms. While in theory the method of using a predetermined mode schedule with time steps as decision variables should work even as the number of contacts grows, I was only able to get problems with one contact to work. Future work on this topic should include expanding this method to a larger range of trajectories, verifying the contact model simplifications I made, and stability analysis for these trajectories. Thank you.